would be fast anonymization of big data streams from Morteza Noferesti from Sharif University of Technology. This paper was supposed to have appeared yesterday in Big Data Science Session 2 on mining and analytics. Right? So he just arrived in Beijing this morning. So whenever you're ready.
Hello to everyone. My name is Morteza. I want to introduce my paper titled Fast Anonymization of Big Data Stream. As a motivation, you know that huge amount of data with high speed generate a new phenomenon that we call it big data. The velocity, the variety, and the volume is its characteristics. The sensor, the social network, and the healthcare application generate a huge amount of data, and we want to process it. Mining and analyzing data generate huge advantage for companies. For example, we can diagnose the illness, we can predicting the user behavior and some things like that. But what is the problem? Why we use it? Why we don't use it? The security problem is interesting in this phenomenon. And the most problem is privacy. There are a lot of privacy problems, and we are going to solve it. But traditional approach are not applicable here. For example, K-anonymity and L-diversity is the approach that we can use it for the static data, but we cannot use it for data. There are a lot of reasons, but the most important is the data stream needs real-time processing, and existing K-anonymity approach are empirical. So we cannot use it for the data streams. Data streams are potentially infinite, fast, and following, and rapidly changing, so we cannot use the previous approach. There are 4 categories that we can use it for data stream anonymization: the cluster-based, the perturbation-based, the tree-based structure, and the counterfeit value-based. But we use the first approach, the cluster-based, so I only describe it here. In the cluster-based approach, each tuple is inserted in the new cluster. Each cluster should contain at least k tuples, and tuples will be published with the cluster generalization. So as the cluster generalization is anonymized, so we can suppose that each tuple is anonymized too. Clusters are used during data stream anonymization, so we have it cached, and the clusters are pushed into the cache, and we use it for the next one. But our algorithm, we call it fast, using parallelism to increase efficiency, and make it applicable for big data stream anonymization. A simple proactive heuristic estimated runtime used to prevent published data after its expiration, because it's important for us to publish data before its expiration time. We introduce a class metric. I will show you in the next slides, and we use more efficient and more effective FATS algorithm. But what is the algorithm? At the first, S is the input stream. Delete the tuples and insert them into set tier. Remove the clusters that they exist and don't exist TKC. TKC is the threshold that we change it during the algorithm. If the number of running threads in the system is lower than the maximum number of threads, create a new thread and set TP to it and call the function publish set TP. This function publish set TP with the minimum information loss. The publish set TP has three lines. First, it removes one tuple and call it T. Then it publishes T with respect to set TP and then terminates the thread that is started for publish T. But the function is as follows. First, is select k-1 unique tuples which are closest to T to choose the best tuple. To choose the best cluster, we can publish T with that cluster. For each cluster in CAKC, which covers T, calculate information loss and select the cluster includes less information loss, call the cluster as CAKbest. If CAKbest exists and CAKbest generates less information loss than GSNU, then we will publish T with CABest. Else, we will publish T with set TP. But if we cannot find, if we have not any time to choose set TP or CAKbest, we can suppress TP and we will publish it. In the suppress, we will lose all the information that is held by TP, and we only publish the data. But we have a heuristic time if the current time minus arrival time plus estimated runtime is lower than the threshold, we can synchronize S and insert TP at the first element of S. So the TP will be published at the next run. But else we can suppress and publish TP. As an example of our algorithm, suppose we have this table. First, we have a bachelor with age 22 and ID 1. We have a master with age 24 with ID 2. We have a non-academic person with age 37 and ID 3. We publish all of them. Now we have this person. We have a data that came from the internet, from a sensor or anything else that generates a data stream with these characteristics, with these attributes. So we have we generated TP with data ID n plus 1 and ID n plus 2 and insert all of them into set TP. Set TP is the data that is published before. We published bachelor with age 22, we published ID 2, we published ID 3, all of them are inserted into the TP. Now we initialize the CNU as ID n with 45 and academic. But JSNU that is generated from the before data is as here because we choose it from this data, and this is the best. This is the closest cluster to this data that is published in this step. And CAKbest is the here because it's more closest to TP. After all of the state of the algorithm, this is the final version of the algorithm. We use a heuristic, a proactive heuristic, a simple heuristic of estimated runtime, prevent publishing of data after its expiration time. The heuristic is as here, the current time minus arrival time plus estimated runtime should be lower than the expiration time. algorithm in a system with Java JDK 7.0.11 and Core i5 system with 2 gigabyte main memory, and the data type collected from UCI University and adult database system. We set K as we initialize K as a 5, quasi identifier size as 10, delta as 30, and TAKC as 20, and number of threads was 5, and the number of A was 0.02. The information loss is calculated with this formula. The information loss is W multiplied by information loss GSC and quasi-identifier. And the quasi-identifier, if the quasi-identifier was numerical, its volume divided by its domain is then the volume of information loss. And if the quasi-identifier was categorical, this formula is used to calculate the information loss. With this formula, our algorithm has the better behavior than the proposed algorithm. The proposed algorithm has the lower information loss, has with respect to data size, has the lower information size with respect to query, has the lower information size with respect to delta, and has the lower information loss with respect to quasi-identifier size. But as the number of clusters instead of KC increases, the information loss decreases. This diagram shows the number of clusters instead of the KC in the duration of the execution of the program with respect to number of threads. For example, when we have 1 thread, the number of clusters instead of KC is the minimum, and when we have 10 threads, we have a lot of clusters instead of KC, and we have a lot of choice to publish our data. When the number of threads increases, the more data we will publish. The information loss decreases too. Because, for example, when we have 10 threads, we have a lot of data published with a lot of clusters instead of TAKC, and this is the proof of our algorithm shows lower information loss. This algorithm shows the execution times of our algorithm is much more better than the number of threads increase, because the threads are is distributed over the 5 cores, so our algorithm is better than when it's executed with a lot of number of them. And we use another formula to compare our algorithm with the previous approach. We use cost COG. It's calculated with this formula, and we have the 2 new parameters to affected the cost. We have publish time and arrival time. So it's very important for us when we publish the data. It's when we get the data, we publish it as soon as possible. So we use these 2 parameters to calculate this effect. When we use cost COG, our algorithm is much more better than the previous algorithm. We have 5 average, we have very better behavior when we have data size, different data size when we have different call, and another. This is our references we use, our important references we use, and thank you.
what kind of privacy disclosure in big data space? In traditional data there are identity disclosure, attribute disclosure. So what kind of disclosure do you want to prevent?
For example, suppose that you have a hospital and you want to get your data to a data publisher center that they process your data and generate some result for you. But you cannot get the pure data to them because the pure data has a lot of information about your customer, and you want to make it something anonymized. You don't want the data publisher understand who has which illness. So you anonymize them, and then you get them to the processing center, to the company that want to process your data. Do you understand?
Are there any other questions? Well,